Hello everyone. Today I'm going to present Tangram, which is a system to bridge the immutable and mutable data abstractions for data analytics frameworks. So distributed data analytics frameworks have rapidly developed in the last decade, from the HPC and to general purpose computing like MapReduce, and then to specialized systems like Prego and parameter server. We can roughly classify offline data analytics frameworks into two categories according to their data abstractions: immutable or mutable. So bulk processing systems such as Spark, MapReduce, and Dryad LinQ adopt the immutable data abstractions, and let's call them immutable systems. One feature of such system is a functional programming model, as shown in the Spark word count. And they use data flow graphs to model the data dependencies among data sets. So with immutable data abstraction, it is easier to support efficient failure recovery and load balancing. For example, Spark used a lineage-based recovery strategy so that only the last partitions need to be recomputed. However, as immutable systems are inherently stateless, they cannot naturally support stateful workloads. Besides, they only support the synchronous execution model. So in contrast, mutable abstractions are usually adopted by specialized systems, such as the Prego and GraphLab for graph analytics and parameter server for machine learning. So let's call these systems mutable systems. The target workloads of the systems are stateful, and the mutable systems usually provide specialized programming models, such as the key-value-based push-pull for distributed machine learning and vertex-centric models for graphs. So mutable systems are efficient for iterative workloads and may support asynchronous execution compared to immutable abstractions. However, it is more expensive to provide robustness with consistency guarantees. Also, those systems rely on the natures of the application for load balancing. Here is a summary of the pros and cons of both abstractions. Existing systems adopt either the immutable or mutable abstraction and do not enjoy the benefits of both worlds. This motivates us to provide a system that can integrate both abstractions into a unified programming model, so that we can transparently determine the data mutability and enjoy the benefits of both worlds. We propose a new programming model called MapUpdate. In the data flow abstraction, like MapReduce, we apply operations on collections and generate new collections. For example, we can apply a map function to a collection A here and generates an intermediate results. Then we apply a reduce function to the intermediate results and generates a collection B. But in MapUpdate, we make data collections mutable. We change the functional reduce operations into a stateful update operation. A MapUpdate program may look like this form with two key operations, map and update. So we can also call this a MapUpdate plan. Collections A, B, and C are map collection, the side input collection, and the update collection respectively. The side input collection here allows the fine-grained key-value-based data access. We can allow zero or multiple side inputs in a plan as well. The map function and update function here are user-defined functions. Map functions are functional and immutable, just as in MapReduce paradigm. And for the update function, it is stateful and allows in-place modification to datasets. MapUpdate provides the following features for expressiveness and for the ability to infer data immutability. First, some or all of the map collection, side input collection, and update collection can be the same. This feature makes in-place modification possible. Let's take a look at the first example. We make the map collection and the update collection the same, meaning that the map collection is being updated. In the second example, we make the side input to be the same as the update collection. Here we use two applications to show how these two designs brings expressiveness. So making the map collection the same as the update collection is useful for implementing algorithms like the vertex-centric graph analytics ones. This is a PageRank example in Tangram. The rank collection stores the vertex PageRank values and is both the map collection and the update collection in the map update plan. And the link stores the immutable edge information. For each vertex, the map function distributes the PageRank value to its neighbors, and the map update function accumulates the partial updates. So in the other example, we make the side input collection to be the same as the update collection. This is useful, for example, in implementing iterative machine learning algorithms. Here, the params collection in the program is both the side inputs and the update collection. It corresponds to the parameter server model. In the map function, we access model in the parameter and calculate the gradients and output the gradients as intermediate results. Then in the update function, we apply the gradients to the parameters. You may have noticed some additional specifications in the example of the last two lines. So this is the second feature of MapUpdate, which supports iterations and asynchronous execution. For each MapUpdate plan, users can specify how many iterations they want to run by set the iteration function. And users can also set the staleness for consistency guarantees. The staleness value here bonds the differences in iteration progress among different data partitions. The third feature is that MapUpdate adopts a simple mechanism to determine whether a data collection is mutable or immutable. The update collection is mutable, and other collections, if different from the update collection, are considered immutable. For example, if all of the collections in the MapUpdate plan are different, only the update collection is mutable and others are immutable. If some of the collection is the same as the update collection, it is considered mutable, like the collection A in the first plan and the collection B in the second plan. The ability to determine data mutability and to express different data access patterns allow MapUpdate to be highly efficient for pipelined workloads, which is also our target scenario. The typical pipelines consist of MapReduce style data processing, followed by various data analytics and testing. Using MapUpdate allows our pipeline workload to achieve comparable performance within each individual tasks to the specialized systems respectively, while we can avoid context switch caused by a unified framework. So we implemented MapUpdate in Tangram with three major system designs. First, we have a controller on each worker node to manage local tasks, and they use partition-based progress control mechanism. We also implemented a context-aware failure recovery strategy. Tangram uses partition-based progress control mechanism to support the box synchronous model, the bounded delay model, and asynchronous execution model. It associates progress with partitions instead of workers. For each update partition, we use a bitmap to record the map partitions from which the updates has been already committed. With this progress control mechanism, Tangram allows different consistency models for iterative workloads, and it provides fault tolerance for mutable data collections. For failure recovery, Tangram distinguishes between two scenarios based on the data mutability, local failure and global failure. Local failure is a case where the failed machines do not hold the updates partition, but only the immutable partitions. In this case, recovery is simple. We can just reload the lost partitions on healthy machines and continue the execution. For global failure, we have failed machines containing mutable data collections. In this case, Tangram rolls back to the latest checkpoint for the mutable partitions and reload the lost immutable partitions in parallel. We conducted experiments with 20 machines in 2 network settings. We designed the experiment to show 3 things. First, how is the fault tolerance performance of Tangram in different failure scenarios? Second, we want to see whether Tangram can attain both expressiveness and comparable performance with specialized systems over a wide range of workloads. And also, we want to see the efficiency of Tangram in handling pipelined workloads. We tested the failure recovery performance in case of both local failure and global failure. For local failure, we tested on the k-means job. We killed a worker storing part of the training data, which is immutable. So Tangram reloaded only the last training data and resumed the iterations quickly. And this is the same behavior to Spark. Note that in mutable systems such as Naiad and Patum, the local failure caused a whole system rollback to the latest checkpoint, which wastes the computation. For global failure, we tested on PageRank. We killed a worker storing rank values, which is mutable, and Tangram rolled back to the latest checkpoint for reconstructing the rank collection. Note that in both failure scenarios, the recovery strategy of either doing the recomputation on lost partitions or trying to roll back to latest checkpoint, it's automatically adapted based on the data mutability. So this doesn't require further specification from users. We also show that Tangram has good expressiveness over different workloads, including bulk processing, iterative machine learning, and growth analytics. We compare with specialized systems respectively for each type of workloads. Our results show that Tangram attains comparable execution time and scalability. We show the pipeline workload scenario where Tangram is most designed for and is most useful in. We compared with using one single general system for the pipeline workloads, as well as using pipelines of specialized systems. We see 2 main benefits of Tangram in such scenario. First, Tangram can achieve comparable performance on individual tasks with their respective specialized systems, like the Tangram compared with Spark plus Patum, and Tangram can avoid the huge context switch overhead. Also, Tangram provides a unified programming abstraction for different type of jobs to be run in a single pipeline. In conclusion, we propose a novel programming model called MapUpdate. The ability of inferring data mutability allows a system to provide both support for iterative and asynchronous execution and efficiency in load balance and fault tolerance. It allows users to express different workloads and achieve comparable performance with specialized systems within one single abstraction. Thank you.
All right, do we have some questions? We serve you here in track 2, sir. You don't have to get up. I wouldn't do this for you in track 1.
Thank you. So I have a question on your experiments part. So in your experiment, in the local failure, you use one workload called k-means, right?
Yes.
For the global failures evaluation, you use a different workload or algorithm. Just
Yes.
like why you just like evaluate them with 2 different algorithms rather than with the same k-means or page rank?
Okay. We use this setting because it's natural for the failure scenario. Let me illustrate this. For k-means, we usually have small case with some latent factors representing each centroid. So the parameters or the model size is relatively small, so that there are more machines containing immutable training data compared to the machines storing the mutable parameters. That's why we can see local failures happening on only the training data machines. And for PageRank, we see that the immutable link values, like the neighbors, is actually co-located with the rank values, which is mutable. So in this case, we can always observe the global failure instead of local failure. Does it make sense? Okay, thank you.
Hi, for the feature 2, you mentioned that you can set the staleness to guarantee the consistency. Can you elaborate a little bit on that?
Okay, so I think this notation of staleness most come from work by Patum, which is designed for distributed machine learning. So the staleness means the bounded delay among the partitions. For example, one partition of the training data can be scanned through and compute the gradients according to the parameters. And this partition may have gone through several scans, like let's say 5 iterations. But within another partition of the same training data, we can maybe have another progress because it's calculated on another worker. And we want to provide a guarantee that the differences in the iteration progress of the workers do not exceed specified values, so as to ensure the convergence guarantee, as well as promoting the hardware's efficiency in doing parallel computation. So if you want to know more about the staleness thing, you can refer to the stale synchronous parameter server paper. Yes, thank you.
We have time for one more question.
So I have a question about context switch. Can you elaborate more about what does that mean in MapUpdate compared to other?
Okay, so let's go to the slide. Sorry. Yes, so here, can I use laser?
Yes.
Yes,
please.
so this figure illustrates the reason of why we have context switch in using different specialized systems. So basically, the normal way of, and the most simpler way of doing the pipeline of different systems is that we let the previous system to dump the data, output data to the distributed file storage like HDFS, and then let a subsequent system to load the data. And this incurs heavy data disk I/O. So this is the main resource of context switch. And we may argue that we can use some different memory-based storage systems or frameworks like Apache Arrow to mitigate this, but this requires a lot of engineering work because we need to confirm to the different formats of the file input and outputs, and as well as the serializability from different languages used to implement the systems.
All right, let's thank our speaker.